Okay, without further ado, I'd like to present Javier de la Rosa, talking about graph databases in Python. I recently did a NetworkX project, maybe used NetworkX in a scientific project, maybe only 10,000 vertices. I don't know if I need a graph database for that, but well, maybe I do? Okay, well, we'll see. All right, let's welcome him to the stage.
Okay, I'm going to talk a bit about graph databases in Python, so thank you for coming. When I know it's Kenneth, Rafe, upstairs, giving a talk to. So first, hi, my name is Javier de la Rosa. I'm from Spain. I did my bachelor and master in Spain in artificial intelligence and pure logic. Then I moved on here, and now I'm doing a PhD in Hispanic studies. So it's kind of weird, but I'm mixing two different fields. I'm working in a Cultureplex lab in the Western University in London, and it's really interesting. So first of all, this talk is a talk at the novice level, so I'm going to talk at very basic level. So if you think you don't understand something, just tell me and I will try to explain it better. So let's get started. In the last 30 years, databases have been relational. That means that all you have to store your data are tables, rows, and columns. So we had a very basic mechanism to make connections between your data. Actually, you only have primary keys that are IDs in your rows and foreign keys. And that's all. That is not very relational. Also, before storing your data in relational databases, you have to define a schema. And if you have ever tried to make a schema migration, you already know that is a big problem, because it's really hard to modify a schema once you have data stored in it. But however, because the data schemas, you can use SQL, that is the standard query language, and it relies in a very strongly mathematical basis because it's the relational algebra. It's really powerful, but it's terrible for highly interconnected data. If you have to make a query using like 4, 5, or 6 joins, a join is when you have to jump between a table to another, that query can take forever, so it's not really good enough for highly interconnected data. And so that's why the community, almost open source community, came up with a solution to go beyond these limitations. This movement was called NoSQL, and it can stand for not only SQL, and then a lot of different kind of databases just appeared. We have document databases like MongoDB. We also have key value store that are actually like huge Python dictionaries, like Redis, Riot, or Dynamo. Big tables like Cassandra, Hadoop for analytics, even the SOAP object database. And we also have graph, like Neo4j, OpenDB, Hypergraph, Tyrant, a lot of them. This is pretty much the current landscape for databases. There are a lot of solutions for every need you can have. But who is using Graph right now? Mozilla, for example, is working on Pancake, and they are using Pacer. Pacer is kind of a query language. Twitter also created a FlockDB. FlockDB is a graph database, but actually doesn't have a query language, so I'm not sure if really graph databases. Facebook is working on the Open Graph concept, and Google, of course, is doing the knowledge graph. So why graph? To understand why graph, I'm going to use the 3 trends identified by Emile Lefranc. Emile Lefranc is the CTO of Neo Technologies, the company behind Neo4j, probably the most famous graph database right now. And he said that data is getting more and more connected, which is true, because at the beginning, in the 90s, we had text documents, then we moved to wikis, we moved to ontologies, to tags, taxonomies, semantic web, and now we have graphs. So that is true. The second trend he identified is the data is getting more semi-structured. And that is also true because now a lot of systems are based in services, and we are using REST APIs, we are using SOAP or even XML. And the decentralization of content generation is a fact. And finally, data is getting more and more complex. You can only think about the Facebook, the user on Facebook, the really huge social network they have, all the way to make semantic trendy like in Twitter. Another current uses, for example, in cloud management or network management, Cisco, I think 1 month ago, replaced all the stored procedures. I don't know if in Oracle, maybe. And they started using graph databases, and they replaced like 100 lines of procedures, only using 2 lines in a query language for graph databases. It's really important also in bioinformatics to make protein folding and things like that. And at the beginning, the first problem was trying to solve graph theory itself is geospatial. I don't know if you know the Königsberg Bridge problem. Was a problem proposed to Leonard Euler to solve, and to solve the problem, this genius came with a whole theory that is called the graph theory. So that's another reason, because graphs are cool, and this is Leonard Euler. So what is a graph? A graph is basically a tuple of 2 elements. The first element is a set of vertices, nodes, relations, and another set of edges. You can also call a graph like a network or diagram. You can also use point, dot, node, or element for mean vertex, and you can also use relationships or line for, say, edge. I will use graph, node, and relationship because I think it's the most intuitive way to do. So basically, a graph states that something is related to something else. There are types of graph. For example, we have undirected graph. It's the most basic type of graph in which you have nodes, a relationship that connect only 2 nodes. If those relationships are directed, we can talk about a directed graph or digraph. If you can find more than 1 relationship between the same pair of nodes, then we have a multigraph. And also, if those relationships are directed, we have a multi-digraph, and things can complicate more and more. We also can find hypergraph in which a relationship is able to connect more than 2 nodes. It's kind of hard to understand, but it's really easy when you see some examples. There are even graphs with their own names. For example, the complete graphs, the stars, snarks, and things can really complicate like log and laughing graph. But don't worry. I'm only just one more type, the property graph. A property graph is a directed, multi-attribute, and relational graph in which every element, both edges and nodes, has an IDs, and also I can use like a key value store for both. So I have nodes, edges, both has an identifiers, numbers, and also I have properties. This is a more formal definition what a property graph is, but in short, a property graph is composed by a set of nodes, a set of relationships, and properties and IDs on both. Sometimes, for example, like in blueprints on Neo4j, relationships can be labeled, what is also called the type. And why is this important? It's important because graph databases are using property graphs to represent and store the data. But this is really, really hard to see, so that's because I'm going to show you an example. How a graph database looks in Python. I'm going to use here the Neo4j REST client. It's a library I'm developing right now. So once you have instanced the graph database objects, we use G, you have a nodes attribute, and then you can create a node using this dictionary of properties. So we can create a node called Sylvester. You can see here. We can also add a new node called Arnold. You can see it here. And then you can create a relationship using this syntax, like Arnold.punches Sylvester. And that's it. That is creating a relationship. And of course, you can add even more nodes, like Chuck. And then, of course, you can add new relationships, like dropkicks. And that's it. So this is pretty much everything about graph databases on a really basic level. But what is the landscape right now in graph databases? There are a lot of options to do graph databases, but if you are using Python, maybe you are going to have some problems. Emerging is a really, really huge ecosystem right now, and in the last 12 months, even more and more graph databases as they are appearing. But for Python, we have some problems because the only graph database with native Python binding is Neo4j, and actually is based on Java. Personally, I don't like Java, and I don't like to use JPipe or something like that to use Python. So the solution right now is using a REST interface to connect to databases. And to do that, we are going to use, for example, blueprints or their own REST interfaces. So what is blueprints, or what is Gremlin? Let me introduce you the Tinkerpop stack. Tinkerpop is, I think it's a European company, and they are building tools and defining like standards APIs to manage and handle graphs. One of the things they are doing is the blueprints. Blueprints is like a standard API to connect and interact with graph databases. And another thing they are doing is Rexter. Rexter is a service you can put on the top of blueprints, and then your graph database is also able to connect through REST. And what about Python? So once you have this architecture in your system, for example, you have your graph databases, then you connect through the Blueprints API. On top of it, you put Rexter, then you have a REST interface, and then you can write your own client to attack that interface. We have Voltflow, and we have PyBlueprints, and we also have Python blueprints. Like Python blueprints is also based on Java, so we are not going to discuss it. This is an example of Voltflow, for example, to create, get, update, and delete elements. You have your object G, then you have vertices, create, the same as Neo4j REST client, for get elements using the IDs, update, and delete. And this is the syntax for PyBlueprints. PyBlueprints is totally based on the Blueprints API that is Java-based. So that is the reason because PyBlueprint is kind of more verbose, but it's useful when you have another kind of databases. But Neo4j, for example, I think is the only one, maybe OrientDB also, that has its own client. So you can connect directly to Neo4j without using Blueprints API or Rexter. And that's what I did. I created the Neo4j REST client, and after that, a guy called Nigel Small also created Python, which is also an awesome client for Neo4j. Once you have your graph database, you define your nodes, you define your relationships, you need to cluster your nodes. To cluster nodes of making into an index, you can use index. After you do that, you can use index to make some lookups. There are basic lookups, like you can see here, for example, vertex index, lookup all the index with the name Alice, and also because Neo4j is using Lucene index, you can do things like this one, using queries and the query syntax from Lucene. But what about more complex search? What about search like I want to know if the friend of a friend is also my friend, or if the friend of my sister is also my cousin? I don't know. So that's because we are talking about traversals. Without traversals, a graph database is only a persistent graph. So let's traverse the graph. A graph traversal is the problem of visiting all the nodes in a graph in a particular manner. There are a bunch of algorithms to do that because it's a really old problem, like A-star, alpha, beta planning, the typical breadth first search or depth first search, Dijkstra, print, float partial. But Neo4j define an API to do traversals. The syntax is not really friendly, it's not really easy to understand, and it's really hard to maintain. So we have, again, blueprints. The guys at Tinkerpop define Gremlin. Gremlin is a DCL, a domain-specific language, for traversing property graph. And the way it works is defining how to do a query based on your current graph structure. You can see there, this is an example of Neo4j REST client using the Gremlin plugin for execute a script in Gremlin. In the script, you can see the G is your graph database object, and then you have the area of Alice, and then I want to know all the nodes related to Alice using a relationship labeled by nodes. It works. You can do almost everything. But Neo4j, again, define another different language that is called Cipher. It's a declarative graph query language. It's more expressive. I think it's more efficient because they care about all the backtracking for you. And it's focused on expressing what to retrieve from a graph. It's inspired by SQL and also by pattern matching. So you define a pattern, and then the language does everything for you. When you want to look for a pattern like this one, node 1 related to node 2 using the label, you can see behind the current syntax of Cipher. It's really similar to how a graph looks like in real. And this is the syntax of a real query. But unfortunately, we don't have time to explain more in deep this. So what are the uses right now? For example, Py2neo is using Cipher helpers to make another kind of function that are not included in the APIs itself. So for example, Py2neo is using Cipher to get or create elements, to get count of nodes and relationships, also to delete elements. And in Neo4j REST client, I'm using Cipher to make complex filtering, really Django style, and it's really useful because you don't have to worry about the Cipher syntax. But if you want to do a Cipher query, you can also use like a casting to return Python pure objects. And this is almost everything. So if I wanted to deploy Neo4j, so you can use Heroku or Amazon. And it's really easy because there are already add-on for Heroku to deploy Neo4j. So you only have to create your application, then add the Neo4j app, get the Neo4j URL, then you create a virtual env, always create your virtual env, and then that's it. Import the library, use the Neo4j URL, and that's it. You can start to play with your graph databases. And this is everything. I think I talk really fast, but sorry. So that's it.
Yeah, we may only have time for 1 or 2 questions because we're behind schedule a bit. No? We're okay? Yeah. Well,
a little extra padding that we don't really need. So.
Okay, step up to the mic if you have anything to ask.
Hello.
Hello.
I'm not by any means really familiar with the graph databases, but I'm just curious. So are the existing graph database technologies, can they easily facilitate stuff like graph analysis, which represents, let's say, state machines? Let's say to make general queries for Markov models and whatnot.
Yeah, for sure. Actually, I'm developing a sub-language in which I use temporal interval logic, and I'm using graph databases to do that. Mm-hmm. And they are using for model checking in circuits, so you can do that, sure.
Mm-hmm. Great, thank you.
Hi, I was just wondering if what the approach would be if you wanted to store multiple graphs in your database and compare subgraphs, for example, within that database. Is that sort of covered with these technologies, or would that be something customized?
No, totally, but you can use Cipher query, for example, to do that kind of comparisons. And there are also predefined algorithms, and you can use.
So it would be able to search through the entire database of graphs to see what kind of...
Yes.
Okay. Thank you.
Thank you. Anything else? That's it.
Okay, let's thank our speaker again.
Relational. That means that all you have to store your data are tables, rows, and columns. So we had a very basic mechanism to make connections between your data. Actually, you only have primary keys that are IDs in your rows and foreign keys. And that's all. That is not very relational. Also, before storing your data in relational databases, you have to define a schema. And if you have ever tried to make a schema migration, you already know that is a big problem because it's really hard to modify a schema once you have data stored in it. But however, because the data schemas...
Okay, without further ado, I'd like to present Javier de la Rosa, talking about graph databases in Python. I recently did a NetworkX project, maybe used NetworkX in a scientific project, maybe only 10,000 vertices. I don't know if I need a graph database for that, but well, maybe I do? Okay, well, we'll see. All right, let's welcome him to the stage.
Okay, I'm going to talk a bit about graph databases in Python, so thank you for coming. When I know it's Kenneth, Rafe, upstairs, giving a talk to. So first, different kind of databases just appear. We have document databases like MongoDB. We also have key value store that are actually like huge Python dictionaries, are Redis, Riot, or Dynamo. Big tables like Cassandra, Hadoop for analytics. Even the SOAP object database. And we also have graph, like Neo4j, OpenDB, Hypergraph, Tyrant, a lot of them. This is pretty much the current landscape for databases. There are a lot of solutions for every need you can have. But who is using Graph right now? Mozilla, for example, you can use SQL. That is the standard query language, and it relies in a very strongly mathematical basis because it's the relational algebra. It's really powerful, but it's terrible for highly interconnected data. If you have to make a query using like 4, 5, or 6 joins, a join is when you have to jump between a table to another, that query can take forever. So it's not really good enough for highly interconnected data. And so that's why the community, almost open source community, came up with a solution to go beyond these limitations. This movement was called NoSQL, and it can stand for not only SQL. And then a lot of, my name is Javier de la Rosa, I'm from Spain. I did my bachelor and master in Spain in artificial intelligence and pure logic. Then I moved on here, and now I'm doing a PhD in Hispanic studies. So it's kind of weird, but I'm mixing 2 different fields. I'm working in a Cultureplex lab in the Western University in London, and it's really interesting. So first of all, this talk is a talk at the novice level, so I'm going to talk at very basic level. So if you think you don't understand something, just tell me and I will try to explain it better. So let's get started. In the last 30 years, databases have been